It's going to record. Oh, fantastic. Okay, so now let's all give a virtual round of applause. So you can use the react button at the bottom for Ivan. And yeah, take it away, Ivan.
Yeah, so basically my research is in nuclear physics, and one of the great things about it is that it has quite a few applications in quite a few fields, as we'll see in a few slides. And it's, as its name suggests, it's the study of the atomic nucleus. But it's also the study of any system made up of any many-body system, a system made out of many particles that interact through the strong force. These include hypernuclei, which are like nuclei, but they contain hyperons, and hyperons are like protons and neutrons, except that one of their quarks is a strange quark. And quark-gluon plasma also, basically, that's what happens when you heat nuclei to really high temperatures, as in trillions of degrees. Or as is accomplished at the LHC and at Brookhaven, collide them at relativistic speeds that's at least in the hundreds of giga-electron volts. And what happens in quark-gluon plasma is that the quarks forget which proton or neutron they're part of and make this liquid. And of course, you might have heard nuclear physics as associated with the nuclear bomb and Chernobyl, but nuclear physics does have something to do with that, but none of the nuclear physics here does, so don't get all paranoid. So why study nuclear physics? As I was saying before, it has a lot of applications in various fields, namely particle physics and astrophysics. A lot of experiments studying dark matter, studying neutrinos, studying the electric dipole moment of nuclei and neutrons. So what is the electric dipole moment? You may have heard who doesn't know what an electric dipole moment is?
So yeah, if you have a question, yeah, just feel free to, I don't know, raise your voice or.
Yeah, so basically, according to the standard model of particle physics, neutrons are supposed to have a really, really small, if any, electric dipole moment, which means that why won't it let me just annotate? Finally, which means that the positive and negative charges would generally not line up like this. But if we can find an electric dipole moment somewhere in a neutron, that's physics beyond the standard model. And some of these nuclei have a structure such that they amplify that electric dipole moment, making them making it a little easier to detect. Also, in studies with neutrinos, dark matter, and their nuclei are targets for the particles being studied. And also in astrophysics, the neutron stars, since they're so closely packed together, you're going to have a lot of strong interaction with them, so nuclear physics is applicable to that. Plus, for the same reason, core collapse supernovae, basically where a star goes supernova because it runs out of fuel, so iron builds up in its core, and at some point it collapses. That iron becomes there's so much iron in there that it suddenly collapses to a point that's no only a little bigger than the size of Manhattan, and that releases so much energy. It is believed, at least, that a supernova happens, and again, that's a very dense system, so dense enough that nuclear interactions are going to play a role. So again, nuclear physics, and of course, nuclear fusion for obvious reasons depends on nuclear physics as well. But from a pure science perspective, it's the fact that nuclei are a many-body system interacting through a strong force. That presents some unique challenges to overcome. And many-body systems are a lot more complicated than few-body systems, like two-body systems or so, because you have to take into account the interactions between the component particles. And most of the time, they're normally solved by treating the system as non-interacting and then adding the interactions as a small perturbation, so to speak, on top of the non-interacting system. This works well for the electromagnetic force, which has a coupling constant of 1 over 137, and the coupling constant is kind of you can think of it as the ratio between the energy density of a particle separated by a certain de Broglie wavelength, and the energy from the electromagnetic force acting over that same distance. So, because that coupling is less than 1, the electromagnetic forces interactions between particles are weak compared to the regular energy of the particles. So those interactions could be treated as a small perturbation to the system, similar to basically enabling us to treat it as an easily solvable linear system. But the strong force is strongly coupled, which means that the coupling constant for the strong force is near 1, which means the strong force's energy is not negligible compared to the non-interacting energy. So you can't treat that as a perturbations. Finally, gluons self-interact. Yeah. Let me pull some of them to draw it. So photons, they just go between charged particles transmitting their forces, but gluons, the particles that carry this strong force, they can self-interact, meaning they split into different gluons. And that turns out to be really complicated and leads to really bizarre stuff. In fact, that's why quarks are never seen outside of protons and neutrons, because gluons self-interact. That means that as you pull apart quarks, okay, I don't know what my mouse is doing.
Wait, what's happening?
Yeah, I'm trying to annotate, but my mouse is acting up.
Oh, I see. Now we can, oh, there you go. Okay.
Yeah.
I was going to say, so what was the intuition for what was the intuition you provided for confinement? Like the fact that you can't see separate quarks? It
Yeah,
was
basically what happens is because because when you separate quarks, you leave a greater distance between the quarks, leaving the gluons more room to self-interact and kind of make themselves, and that self-interaction actually makes the force stronger. Okay, I don't know where Rahul went,
oh,
but
still here.
but be hello?
Oh, can you hear me?
I can hear you.
Yeah. Awesome.
Sorry. So because the strong nuclear force gets stronger as you pull apart the quarks, you 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 can't really pull apart the quarks. So eventually you come to the point where you pull apart the quarks so much that you store enough energy into pulling them apart that energy is enough to make a quark-anti-quark pair.
Oh, so basically you're saying since gluons interact with one another.
Yeah, these gluons interact with themselves and with one another. The strong force becomes stronger
As
with
you pull
greater
apart the
separation.
yeah, I see the intuition. Okay.
Not weaker, which is required in order to fully escape, like with gravity. Okay, let me try erasing the marks I made. So we have a system that's pretty hard to solve right here because it's nonlinear and has a lot of bizarre behaviors. So what we can't solve analytically, we can solve computationally. So thought Mike Kreutz at the Brookhaven National Lab back in the 70s. So he created this system called LATTICE QCD to do just that. Create a lattice using a computer as in a grid, and put the quarks on the corners of that grid and put the gluons on the links between the points on the grid, and then run a Monte Carlo simulation on that computer. Basically, you run it over all possible paths of the system, which you have to do in quantum mechanics because normally in classical physics, a particle follows a set path. Physicists call it the path of least action for reasons you'll learn in 105. But the point is, there's a specific path that a classical particle would prefer, but that's not true. That's not true with quantum particles. Instead of following a direct path to point A from point A to point B, pretty much any path could from point A to point B is technically possible, The only difference is some paths are more probable than others. So you basically have to run through all of the paths of the system up to a certain degree of accuracy which means all paths that have at least a certain threshold of probability of happening, and then basically integrate over them. And from the results, you find so-called correlation functions, which are the expectation values of and there are two kinds of correlation functions. 2-point, which you basically multiply the observable of the particle at the final point times the observable of the particle at the initial point, to take the mean or the expectation value of it. But that's a 2-point function. It's for basically gauging the state of the particle at creation within the system to its annihilation within the system, for lack of a better word. A 3-point function is used to model interactions. So it's used to model a system where a particle is created at point A, it propagates, and then at some point in the middle of its path, it experiences some interaction O, and then after which it goes to point B, at which it's annihilated within the computer. So the correlation function for that would be a 3-point function. Basically, you multiply the operator that generates that interaction, which you'll learn about in 137a, times the state of the particle at its creation point times the state of the particle at its annihilation point. Now, what do I mean by the state of the particle? It's basically the operator that's used to either create or annihilate the system. Create at the starting point or annihilate at the end point.
The intuition here is that like these 2-point functions measure like probabilities for particles to propagate from like location to location. And then 3-point functions sort of measure the probability that a particle will do this propagation, but will undergo some process in the middle, basically.
Yeah, thanks, Rahul. So
that was a question.
Well, yeah. Oh yeah, there's a question.
Oh, is that correct or is that incorrect?
That's correct.
Oh, okay.
So LATTICE QCD is not without its challenges. In no small part due to the fact that you have to simulate all possible paths. The number of computations you need gets higher and higher and higher exponentially. That means that in order to simulate a system for, if you want to simulate a system for a certain time t, and it takes you say 5 seconds, and then you simulate it for 2t and it takes you say 10 seconds, in order to simulate it to 3t times, it would take you 20 seconds, 4t times 40 seconds, and then 100t times, it would take you in T10 100 times, it would take you over 10 to the 30 seconds, more than the age of the universe. And the signal to noise ratio encounters a similar problem as well. It gets exponentially worse with time as well. But, which puts a
What do you mean by
pretty big,
signal to noise ratio here?
yeah, basically, signal to noise ratio defines, it's not quite rigorously defined, but it's basically the ratio of the interactions that you you want the you want divided by the amount of interactions that are not supposed to be there, that come from the that come from stuff you leave out, or just simple system noise that you can't get rid of within your computer, say because your data format is only accurate up to a certain amount of decimal places. Now, recent advances in technology are pushing the boundaries set by those limitations. And in fact, quantum computing make a might get get rid of a lot of these obstacles altogether, its its signal to noise ratio and the number of computations needed, it uh, gets worse by a polynomial function rather than exponentially, which means which basically means that it gets worse a lot slower. So, but nonetheless, for now, we're kind of stuck within limitations. We can't even simulate multiple nucleon systems beyond, say, 3 nucleons directly with lattice QCD. So what we do is we do lattice QCD simulations in relatively easy to compute systems, like 1 or 2 or so nucleons with a bunch of pions, which within nuclei carry the strong nuclear force between protons and neutrons. And then after doing those lattice QCD simulations, we extrapolate them to the systems that we want. And as part of that extrapolation, we have to extrapolate to physical pion mass, physical, an infinite volume of space, and a continuous lattice spacing, because these computations are often easier to carry out with a pion mass that's different from what it is physically, and you can't simulate an infinite volume of space on a computer. You can't simulate points that are infinitely close together on a computer, because you need an infinitely powerful computer for that. So to extrapolate, the lattice QCD results are fitted to effective field theories, which unlike, say, the theory of everything that a lot of particle physicists are looking for, which describes fundamentally the laws of physics of the whole universe, effective field theories are theories that work in a set situation. In our case, what we're looking for is interactions between nucleons, protons and neutrons, pions, and whatever else our system interacts with, depending on the application. Like, it could be neutrinos, it could be dark matter. So in order to use those effective field theories, we have to fit them to data from last QCD. And most of the fits that you're probably familiar with is based on an interpretation of probability that's frequentist. That is, it defines probabilities as, say, as if a probability of getting heads on a coin is 50%, that means that if you flip that coin many, many times, half the time you'll get heads. And for an experiment, what that means is that a fit is a prediction that in an experiment within which an experiment repeated many, many times will fall within, say, within 1 sigma of 68% of the time, where a sigma is a standard deviation of the fit. This works well if we have lots and lots of samples, but it's pretty hard to get many of the same sample here. Plus, if you ask Professor Hedeman, frequentist probability doesn't really work with quantum mechanics. And I don't know if that latter part is relevant, but for our research in this field, we use fits based on Bayesian probability, which are subjective assessments of the likelihood that something will happen. As usual, probability of 0 means it will never happen. Probability of 1 means it will always happen, but between those two, a Bayesian probability is just a degree of belief. And the really neat thing about Bayesian probability is that current assumptions about probability can be updated based on new data using Bayes' theorem, which I've written down here. So here is the belief. Here's the probability that we believe our parameter theta will be. This is the probability distribution of our parameter theta before we do our experiment. And this is after we take the data x, which has a probability distribution x, p of x, yeah. And specific techniques that use Bayesian probability include the Bayesian least squares fit, as well as also we use machine learning. Yeah, thanks for the reminder, Rahul. I better pick this up. Yeah, so the Bayesian least squares fit. So basically, right here is the probability of right here's a probability distribution based on whatever we plug in our model, and p of theta is the so-called prior distribution of the parameter set as discussed before. It's what we believe the probability distribution of our parameter to be before we take our data x. And p of theta given x is the posterior. That's a probability distribution of our parameter after we take data x. And p and that posterior can be solved either directly or more commonly the problem is reframed in terms of minimizing this scaling factor, which corresponds to the exponential term of a multivariate Gaussian, which is like the regular Gaussian that you're used to. You know, that bell curve distribution, but with not just one parameter being varied, but many. In a multivariate distribution, this x isn't a single number. It's a vector or a matrix.
So is the intuition here that like each component of the Gaussian distribution, or like, no. So the intuition is not actually that each component is a Gaussian distribution independently.
No. No. That's true in some cases, but not in all. You see that covariance matrix marked cov? Yeah, this mouse is pretty hard to handle. I can't see my mouse. You see that?
Yeah, I see it. I see it.
Cov?
So basically, if it's diagonal, then what I've said is correct. But if it's not, then
you also have just the regular Gaussians of each variable, but also interactions, so to speak, between the different between the different distributions of the different parameters. Okay, I can't find my mouse again. Not ideal, but this works. So the main effective field theory that we use is chiral perturbation theory, which basically again treats our situation as interaction between nucleons exchanging pions. This is the description at its most basic, but how it models those pions is basically it models them using spontaneous symmetry breaking. So for massless particles, physics is the same for right and left chiral particles. So what is chirality? You may have learned in, say, if you've taken a biology class, you may have heard an analogy between learn about chiral molecules, in which left-oriented molecules are actually interact differently than right-oriented molecules, and in physics, kind of like a left and right hand. Let me disable screen share for a moment. Basically, you have a left and right hand overlapping like this, but they don't exactly overlap. I have for the right hand, the thumb's here, and my fist, the fist with which I can grab my calculator is here, but it's the opposite way with my left hand. The fact that these two act my left and right hand acts a little differently, that's kind of the essence and the intuition behind chirality. I just talked about something that someone who's taking a biology class might know about if they've taken a biology class. But in physics, that different behavior between so-called right-handed or right chiral particles and right-handed or right chiral particles is that the is that a certain quantum mechanical property related to angular momentum called spin, when basically when spin the thing about spin is that it can be evolved along complex space, like so. It's basically a particle with a spin 1 could be rotated, could be so-called rotated, so that its spin would become 1 plus I over root 2. And then it could be further rotated, so there would be I, and then further rotated, so there would be minus 1. But where the chirality or the handedness of a particle, left and right-handedness, is that where a right-handed an operator that for a right-handed particle would transform the spin counterclockwise. I mean, from 1 to I to -1 to -I to 1, would transform a left chiral particle spin the opposite way. And for massless particles, physics is the same for both kinds of particles. For those particles whose spin transforms counterclockwise under those operators, and those particles whose spins transform clockwise. But for quarks, this actually isn't exactly true. The laws of physics are slightly different. So this symmetry is broken. So one way to treat a broken symmetry is to treat it as spontaneously broken, where it holds normally, but then can just spontaneously not exist anymore. A common analogy to that is if you stand a pencil on its tip on a table, if you look at it from all sides, a pencil standing on its tip will look the same in any case. But once you let go of it, it automatically chooses a direction to be in, and it won't look the same in all directions. The spontaneous symmetry breaking works the same way. When the chiral symmetry of quarks is broken, the chiral symmetry of quarks is treated as a real thing, but that can automatically be broken. What happens when it breaks is that a pion gets released. So that's how pions are modeled. And then that's combined with a theory that treats nucleons as elementary particles, and you get our good old theory. So using this framework, we've measured the ground states of 20 different baryons. Baryons being particles that are made of quarks, be it protons, neutrons, and those hyperons we talked about earlier. We found the ground state energies of them. And we also found okay, this should be neutron proton mass splitting, but due to a typo, it says electron proton mass splitting.
Ivan, we can't see your slides. Are you pointing to something in the slides?
Yeah, I am.
Oh, I see. We can't see them right now.
Uh-oh. Yeah. That should fix it, right? Did
Yes.
that fix it?
Yes, it did. Yeah.
Yeah, so. And also lattice QCD is now routinely used to determine properties of mesons, which are particles made of one quark and one antiquark, and which often carry the nuclear force between baryons. And near future work is extending our studies to multi-nucleon interactions, taking advantage of the fact that our computers are getting better and better. And also understanding nucleon hyperon interactions. A hyperon, like I said before, is like a proton or neutron but has a strange quark in it, and which is pretty important to understanding neutron stars because strange quarks are thought to be common in neutron stars. And also improving precision on this so-called axial vector current interactions, which are important to understanding the weak force. What is axial vector current? Basically how interactions work is that in quantum field theory in general is that they're solved by invoking some conserved quantity or Noether current from Noether's theorem, from which a lot of symmetries are found, and hence the current. What about the axial vector? Well, when you reflect, say, a velocity vector across the x-axis, it will point the same way. But when you reflect it across the reflect, say, angular momentum across the x-axis, it will point the opposite way. So there are two kinds of vectors. The kind of vector that, when reflected, points the same way as it did before, which is just called a vector. And the kind of vector which points the opposite way, when reflected, that's an axial vector. Now, the weak interaction contains both the axial vector and the vector current components. So in order to help understand the weak interactions, my current work is on the axial vector current interactions within the weak force, and also including quantum electrodynamics within lattice QCD, because we've kind of managed to get away with not including that because strong force is a strong interaction, but now we need that in order to improve precision of the proton-neutron mass splitting, among other things. And I think that's the end of the story for now. Any questions?
Does anybody have any questions? Don't be shy. If the chat is more convenient, you can just put it onto the chat. How about this? If people don't have any questions, react in some way. Like there are two reactions at the bottom. Like, you know. Okay, Ben does not have. Okay, I'm guessing Nicholas is probably not here, because he said he wasn't going to be here. Oh, he is.
Oh yeah, we have questions. Never mind. These are the previous comments.
Yeah. Nicholas does not have a question, but did not feel like reacting. Okay. Regardless, Ben has a question. How are you, Ivan? I guess that's a. Regardless, I think let's all give Ivan a round of applause, and how you do that is just react with the. Nope, not this one. this one. Um, I hope you guys enjoyed this. This is sort of this is sort of an a bit of an avant-garde format from what we're used to. And yeah, but we're gonna still try to provide some exciting seminars for you guys. On the bright side, we can include seminars from people that aren't at Berkeley, and and also I think maybe we can perhaps ask a bit more questions, because maybe it's scary to say things when you're face to face with someone, but behind a computer screen it might be a little bit easier. Regardless, yeah, I hope you guys enjoyed. If you guys are interested in giving an undergraduate seminar yourself, please contact ucbsps@gmail.com. A recording of this will be up on the SPS YouTube channel, and the link to that will be on the next SPS email. But yeah, thank you guys so much for coming. Who's doing the next undergraduate seminar? So Shaunak messaged me with a saying that he was interested in doing it. So Shaunak does some work on cosmology. So if you guys are interested in that, stay tuned. Alternatively, there are a couple of people from Harvard, one of which is Ryan Samina, and the other one is Alec Douglas, both of which wanted to maybe give a joint undergraduate seminar on their work in Misha Lukin's quantum optics group at Harvard. In particular, they were interested in talking about some cool physics you can see when you have in diamonds, effectively, when you have a very strong concentration of what's called of nitrogen vacancy defects in diamond, and you could do quantum computation using that. So yeah, for those of you that are interested in quantum computing, I would recommend coming. If Shaunak can't give it next week, then I'll try to get these guys to give it next week. Yeah, Ben just responded okay in the chat. Okay, but yeah, thank you guys so much for coming. I hope you guys are doing well. Yeah, toughing through the quarantine. Hopefully we can see each other in person at some point soon. But yeah. Where are my glasses? Can I see? I can see because I'm standing so many feet away from my computer. Yeah, anyways, I'll see you guys later. And yeah, thank you guys so much for coming.
Hope you like my presentation.